Here's the 7.8 to 7.10 screencast. Seven point eight is on representations of equilibrium, and the learning objective is represent a system undergoing a reversible reaction with a particular model. So the essential knowledge is we just want to be able to look at and understand or draw potentially a particle level drawing that represents equilibrium. Kind of the couple key things here. Remember, at equilibrium, you have constant amounts of each substance. So if you just take one snapshot of what's going on, you can't tell anything from that. You have to have particle level drawings from different times. And basically what you're looking for is, do you have the same amount of each component from time 1 to time 2? And if you do, you're at equilibrium. So in this example right here, it looks like you're going from a solid to a gas. From this point right here, I mean, it tells you that you've established equilibrium. But if it didn't say that, you could look and see, well, do we have the same amount of each component? And it looks like we do. So from here to here, we've reached equilibrium. We're at equilibrium. But if you're changing the amounts, like if you go from here to here or from this situation to there, we have different amounts of each component. We're not at equilibrium. So that's how you can tell if you're at equilibrium or not. You have to have at least 2 snapshots at different times to be able to tell. 7.9 is on Introduction to LeChatelier's principle, and the learning objective is identify the response of a system at equilibrium to an external stress using LeChatelier's principle. All right, and then for the essential knowledge, we want to be able to apply LeChatelier's principle to different reactions and determine the direction of shift and what effect that has on measurable properties. And by measurable properties, we're talking about concentrations or we're talking about pressures. So with LeChatelier's principle, the situation is you're at equilibrium. Equilibrium has already been established and some stress is applied to the system, as in it's being changed somehow. And LeChatelier's principle states that the system will respond in order to get back to equilibrium. So we want to figure out, well, which direction is the reaction going to shift to compensate for the stress and get back to equilibrium? So the different situations you got to know. We have to know what happens if you're changing the amount of some component. We want to know what happens if a pressure is changed or volume. And you want to know what happens if temperature is changed. So for this example right here, let's say if we increase the amount of nitrogen, the reaction will want to shift right. So if you, and I'll just summarize it up here. So if we increase some component, so if there's an increase of a component, the reaction will shift away. So if we increase the amount of nitrogen, that means the reaction will shift to the right and the forward reaction will be favored at that point. The forward reaction will be faster until it gets back to equilibrium. So if you increase a component, it's going to shift away from that component. If you decrease a component, then the system will respond by shifting towards that removed component to get back to equilibrium. Okay, so if you decrease a component, it's going to shift towards that component. So if we take away, if we're at equilibrium and we take away some hydrogen, the reaction would shift to the left, or the reverse reaction would be favored until we get back to equilibrium. If you increase pressure, the next stress, so you increase pressure. This could also be stated by decreasing volume. It's the same thing. Pressure and volume are inversely proportional. So if you increase pressure, it's going to shift towards the side with fewer moles of gas. So if we increase the pressure for this example, we have 1 mole of nitrogen, 3 moles of hydrogen, and on the reactant side, and 2 moles on the product side. So in this case, if we increase pressure, it's going to shift to the right. Then the last one, temperature. Now for increase in temperature, it depends on if it's endothermic or exothermic. In this case, we have a negative delta H. That means it's an exothermic reaction. So if it's exothermic, we treat, that means heat energy is being released. So we treat heat energy as a product. If it was endothermic, if we had a positive delta H, we'd treat heat energy as a reactant. And now we just treat it like in these first two situations. So if we increase temperature, it'd be like we're adding more heat and it's going to shift away from this. So if we increase the temperature for this example, the reaction would respond by shifting to the left. Okay, and then you also want to be able to graph this out or interpret graphs of LeChatelier's principle and how the system responds when a stress is applied. And there's a couple different situations. It could be concentration versus time, like this drawing over here, or it could be rate versus time, like this drawing over here. So now both of these graphs, we're increasing the amount of reactant. So the reactant is going up. In the case of the graph on the left, we're increasing, we're using this equation right over here. We're increasing at time t how much nitrogen we have. So that's the stress that's applied. So we increase nitrogen at time t. So nitrogen is a reactant, so the reaction will shift to the right to get back to equilibrium. So that means after you add that nitrogen, reactants will get consumed and you'll get more product until we get back to where we're at equilibrium again. So with these lines plateau. At this point right here, can't see it very well, but at that point, that's where we reached equilibrium again. Okay. In the case of rate versus time, it's the same concept, but remember at equilibrium, the rate of the forward reaction and the rate of the reverse reaction are equal. So here we're at equilibrium. At this time right here, hydrogen is added. So again, the reaction will shift to the right to get back to equilibrium. So the forward reaction is favored, but as we proceed towards our new equilibrium, the forward reaction slows down, the reverse reaction speeds up until you've established your new equilibrium conditions. So at this point we have equilibrium reached again. So just keep in mind that, remember, at equilibrium, what's equal is the rates. Okay, so rates are equal to equilibrium, but not necessarily concentrations. Concentrations are constant, but not necessarily equal. Okay, and the last section for today is 7.10, reaction quotient and LeChatelier's principle. And the learning objective is explain the relationships between Q, K, and the direction in which a reversible reaction will proceed to reach equilibrium. So the essential knowledge is a disturbance to a system changes either Q or K. So if you're at equilibrium and some stress is applied to the system, either Q or K will change. When you're at equilibrium conditions, Q is equal to K. When you're not at equilibrium, these two are not equal. So when a stress is applied to a system, one of these two will change. Now, stresses that change Q, those are changes in concentration or changes in pressure. Changes that will change the K value, that's temperature. Okay, but either way, if there's a disturbance or a stress applied to a system, it brings Q and K out of alignment, or it makes them unequal. And then the system will always respond in a direction that will move Q towards K until you've reached a new equilibrium condition and these two are equal again. And that's all for today's screencast. Have a great day.